ability to initialize the state of the qubit. Okay, how about the decoherence time? We take it for granted, right? I'll talk about measurement. How do you know a qubit is spin up or spin down? So it's difficult to measure the spin. Because why? Because spin, in order to measure spin, you actually need to apply magnetic field to see how it changed the energy, right, of the system. Maybe you need another spin to measure the spin. Just think of that, it's not easy. But we are very good at measuring charge. So one of the ways is to do the so-called spin to charge conversion. Okay, spin sensing is difficult. So here, let's look at a system. This is not silicon qubit, okay? This is an aluminum gallium nitride system. We don't have chance to go into details, but you just trust me, right? If you know some of the free fine material system, you probably understand what it is. We have a wide band gap aluminum gallium arsenide next to a narrow band gap gallium arsenide. It's okay, you don't know what it is, I won't test it. But the point you need to know is you create a quantum dot in the vertical direction. That is how you confine it. When I presented this picture, some of you might already feel uncomfortable. Yeah, the barrier might be able to form the confinement laterally, but vertically, I don't see any confinement, right? So we can use potential well, and one of the way to do the confinement vertically is to have this. And if you're not very familiar with the silicon or transistor, that is okay, right? They are too much for you to learn now. What I'm saying is this is the cut direction. If I call this XY, and that is what we are cutting, XY. We are looking from top to bottom. I'm cutting here. So first I hit this aluminum gallium arsenide, which has a wide band gap. And then gallium arsenide, which is a nano band gap. And then as a result, we form a two-dimensional electron gas. So I can confine it in the vertical direction, and then plus other gate, I can confine it in the lateral direction. Then I just like creating a three-dimensional potential box. Okay, and then I can use, and then what do? This is what they use in this paper. This one is looking from top. This is the bird view. You will see this pretty often in semiconductor, right? This is looking from the top of the device. So what does it mean? This is looking, it means this, you're looking from the top. This is your eye, okay? And this is the bird view. Is this okay, what I'm talking about? You're looking from top, are you okay? Right, so this is the pattern. Again, we don't want to go to detail, but you take it for granted. I do create a quantum dot. Of course, there's a lot of engineering, a lot of physics here. But with this gates, lateral gates, right, it's not as simple as the plunger gate here. But because this plunger gate is not going to work, you need to have a two-dimensional confinement laterally. This is just a simplified structure. But basically, you have a gate here, gates here, gates here. So in this region, you basically confine the electron, right? If I make this very negative, your electron cannot leave. And you do it at the right potential, you have only one electron. And then vertically, you will say, will you go into the paper, right? Vertically. It means will it go down? No, because we have this triangular potential well confining it. So I'm showing all this is just want you to trust me that yes, we can confine an electron in 3D space inside this semiconductor. And you just trust me, right? If you don't, I can explain more to you by drawing a better picture if you talk to me, right? Otherwise, the goal is just that I confine a qubit here. So qubit is here. So here is the qubit. Right? This is the qubit. That's the first thing. Now you also see that I have what? A reservoir. A reservoir basically is just a metal. It is not shown here, right? Or it is buried. The SE as EM image cannot see it. And we also have a transistor here, right? It doesn't show the transistor, we cannot see the transistor, but basically here I have a transistor. This transistor is called, not really transistor, quantum point contact transistor. It's a transistor, quantum point contact transistor. So it's designed that the current is super sensitive to the potential around it. For example, if I have an electron inside this quantum well, the current will be much smaller. If I don't have an electron, the current will be much larger. Are you okay with this? Right, so I have a setup, classical, to confine one electron here. It is next to a reservoir that allow it to do tunneling between the reservoir, similar to what we said here. Okay? This barrier is just because you have a distance, right? At the same time, it's next to a transistor called quantum point contact transistor. Right, let me write here. QPC is quantum point contact, right? And we don't discuss this. There's a lot of physics, right? But all you need to know is just it is like a Schottky, point contact, and you have a large potential barrier. So if you can lower the potential barrier by a little bit, the current will tunneling current will increase a lot. So it is very sensitive to whether you have a charge next to it or not, right? So if I have a electron here, negative charge, then it will make the current very small. If you don't have an electron, then the current will be much larger. So here we did not talk about spin yet, right? But if I can connect spin to charge, for example, if spin down means I don't have if I can convert spin down to be having not having an electron, then I have a large current. If I can convert spin up to be having an electron, then I have a small current. By measuring this current, then I know whether I have an electron or not. That's called spin charge conversion. So still very confusing. Let's take a look exactly what I'm talking about. And the scheme is the same as the possible initialization I mentioned earlier. If the electron here is spin down, means it has a higher energy. Okay? The magnetic field is pointing down, right? The magnetic field pointing down. So spin down means that I have higher energy. It is next to the reservoir. Because it's at cryogenic temperature, this is empty. So this will tunnel to here, right? Is this part okay? If it is spin down, it has high energy, so it will tunnel. Now what happens if you remove the electron? I just told you, because it's less negatively charged. So the point contact transistor will have a larger current. So when it just tunnel, I will see the current goes up. But after a while, the electron from the reservoir will tunnel back, right? Because this is empty and I have enough electron with the energy. So once it tunnel back, I have a negative charge, then the current will go down. So in the experiment, I will see a bump in current. It doesn't matter. I don't need to calibrate this well. I just want to see if I see a bump in the current measurement. You can refer to the paper I cited in the book, right? See how they measure it. It's noisy, but you can see it. Now, if my electron was spin up, which has a lower energy, it can never tunnel because it doesn't have enough energy to go up, and at the same time, those below Fermi level are filled up, so it cannot tunnel. So your current will be just a constant. It never change because you always have an electron here. And that is the so-called spin to charge conversion to read out the spin state of your qubit. Let's pause a little bit. Any questions? Is this clear to everyone? Looks like this is clear. If not, just ask me later, right? So, very good. We can do